Yeah.
I'll give you 5 after 15 minutes.
Yes. Good afternoon, everyone. I'm Xiao from ETH in the Machine Learning and Computational Biology Lab, PS Custom Bookworld. Today I'm going to talk about a project we're recently working on. It's called Kernelized rank learning for personalized drug recommendation. So we're all talking about personalized medicine. Let's review about it. So we assume that many diseases are rather heterogeneous, and we want to recommend the most promising drugs based on patients' molecular profiles. And we would like to use the patient database and using machine learning models to do this recommendation. So let's assume we are learning from a hospital knowledge bank where we have a bunch of patients, and we know their molecular profiles like gene expression, methylation, and so on, and also some of their treatment history. Let's assume cancer. Then we know there's each column here is a drug. Then we know some drug responses for these patients. Some of them have good response, like CR, complete response. Some of them doesn't work, and it's stable disease or progressive disease. Then we want to recommend the new therapies, the most effective therapies to the new patients if we know their molecular profile. This is the whole idea of personalized medicine. So how can we do it with machine learning? If we have the X as the molecular profile of the patients, we have N patients and P molecular features, where Y is the drug response for the D drugs measured on these patients. And then we are going to learn a predictive model, W, so that X times multiply W can approximate Y. Then afterwards, if you have a new row coming with the new X, the new X times multiply W, we got the predicted drug response for the Y. However, it depends on how you approximate this one, right? If you treat it, if the idea is to predict the exact drug responses for each entrant, then we can use the mean squared error to measure the approximation between Y hat and Y if you have a Gaussian prior on the on Y. However, this is to predict the drug response for the cancer cell lines of patients, but to recommend the drug, we cannot do it directly. We need to predict the drug response for the new patients for all the drugs. Then you have to sort all the drugs. Let's say larger value means better response, and smaller value means no response. So finally, after you predict all the drug responses, as what has been talked before for the drug sensitivity prediction, you predict the drug sensitivities, still you need to sort all these values and recommend the top 3 or top 5 drugs to patients or doctors for them to choose. So this is become 2 steps of the final drug recommendation problem. This may not be very suitable for clinic dataset for the following two problems. First, it's very sparse. For the cancer cell line, the model cell line datasets, we have hundreds of drug responses per cell line. However, for the real patient datasets, we may have only a number of drug treatments, 2, 3, 4, 5 at most maybe. And the other one is this dataset might be imbalanced. When talking about imbalanced, we assume that doctors have some prior knowledge to prescribe the drugs to the patients. Maybe some drug was better for this type of cancer, or we know doctor knows some gene mutation of patients, then he can prescribe the target therapy to the patients. Therefore, we propose to use learning to rank model for drug recommendation. We directly we predict the relative rank between drugs, not the exact drug response values. So we are trying to answer the question, which drug works better than the others, rather than how well a drug will work. And finally, we recommend the drugs rank at top. So to do this, we change the loss function of mean square loss function in the former formula to the ranking-based loss function. We use the discounted cumulative gain for ranking. The idea of this function is to weight drugs differently. So it's what in this it's short for DCG of f and y. F is a prediction, and y is the true response, a row, a vector of for one patient. So that this is the sum of all the D drugs of this term. So the nominator term means that if a drug has a higher value, it will have a higher weight. The denominator means that if a drug is ranked higher, it has a higher weight. So intuitively, if a drug have a higher value of drug response and it ranked higher, you will have a larger gain. So this is a gain function. We convert it to a loss function since machine learning methods usually do the minimization instead of maximization. So this is the object function we would like to have. The NDCG, it's just normalize the DCG value, which belonging to 0 and y, 0 and 1. Then 1 minus this one, just the loss function. And the next term is the regularization term on the learned feature matrix. This is the new objective for the ranking problem. However, this loss function is non-convex and non-smooth, which means the optimization is very difficult. So when we have this case, non-convex, non-smooth problems, what you usually do is convert it to a convex problem or smooth problem. So what we do is we use a convex upper bound of this NDCG loss, 1 minus NDCG, and minimize this convex upper bound. So for the optimization, this for our initial result is what's better than the smooth version of an ECG. So this next slide shows the convex upper bound of the NDCG loss. So we first rewrite DCG of Fy to a dot product of two vectors A and B, where pi is a permutation of all the drugs. So A is just the denominator, and B is the numerator, and pi is permutation of the drugs in F. So then a convex upper bound can be defined as this function, which include a maximization subphase, and then they have a C, which is a decreasing in this case. So finally, we integrate this convex upper bound to the ranking objective function, and then we have this new convex problem. Similar as before, just using the convex upper bound. And we do the kernelization to capture nonlinearity in the data sets. Just let W equal to X transpose times beta, and replace X times X transpose by the kernel matrix. And this comes with our final optimization problem, which is minimize beta on all the samples of the convex upper bound and DCG loss function. And the regularization term also turned from the Frobenius normal to the normalization on kernel matrix. For the optimization, we use the bound methods for regularized risk minimization. This is if you have a convex problem, each iteration you minimize the convex upper bound, you minimize the lower bound of the linearization and the gradient, and then each iteration you cut off the plan of the searching space, and later in a few iterations we will have a upper bound of the convex problem. So to illustrate BMRM, given the convex function, the convex loss function, the convex regularization function, and the W, a vector, we can, for each iteration, compute the gradient of the loss function, and then update the lower bound function, GW, which is which is the maximization of the linearization of the dot product. And then we minimize this linear bound. So this is a minimization problem involved with a maximization sub-maximization problem, which is difficult to solve. So in paper proposed in machine GMRL in 2008, they proposed to solve it in the dual form by integrating Lagrange multiplier. And so alpha can be solved in, this is a quadratic programming problem, and A is the subgradient at each iteration. So each iteration solves a quadratic programming problem with the points of T is iteration. So it's much faster than the other, the prime problem. So to extend it, so here we only consider the vector of W, the original paper. We extend it to, here beta is a matrix. So it's instead of vector and object function, it's regularized on a kernel matrix rather than the L2 normal of the vector. So we extend it by applying a trick, which means that beta can also be decomposed by column. So the trace of beta transpose multiply k and multiply beta can also be decomposed by the column of beta. And then I can also show that by introduce the Lagrange multiplier, this can also be decomposed in the dual form, and also it can be solved in dual form. So we would like to test the data testing methods on the hospital patient data sets, but we don't have it yet. So we test on the model data set, which is the previous speaker have talked about it, the genomic drug sensitivity in cancer data sets, where there are 1,000 cell lines and 265 compounds. And the drug response is measured by the IC50, which is a concentration of a drug that inhibits 50% of cell growth. And there are 4 types of genomic profiles. We use gene expression, which is the most effective one, most predictive one among them. So we can also integrate all of them, but we didn't do that yet, since the aim of this project to show ranking, the power of ranking loss, not integration of data sets. We compare to a bunch of regression-based methods, including the state-of-art single task approaches, elastic net, random forest regression, kernel ridge regression, and one multitask approach, which is kernelized Bayesian multitask learning, which won the Dream Challenge that mentioned before. And also our proposed methods, kernelized rank learning, short for KRL. And for evaluation, we evaluate for 2 metrics. The first one is called NDCG. This is what we optimized. The other one is precision K. So we only consider of the top K predictions. If you recommend 10 drugs, 5 drugs, then you go to ground truth, also pick up the top 5 drugs, and you compute the overlap between these 2 sets, and you compute the precision based on that. And NDCG is also computed on the top K ranked drugs. Sorry. So here are some results on the GDSC datasets. For the full training datasets, which means that we have around 220 something drug response per cell lines, our methods, the right bar works better than the single task methods and comparable to the multiple kernel methods. For precision at K is sometimes better. So here the left is right is NDCG K and left is precision, right is precision at K. And in the X exercise, it's the number of K to be evaluated, which the top 1, top 3, top 5, top 10 to be looked at. However, this is on the training datasets. This is on the full training datasets, which we think is far from the realistic clinical setting, where you have each patient only have a number of treatments. Therefore, we do a simulation to subsample the data sets so that it's be closer to the real scenario. We sample 5 drugs per cell for training and keep all the responses for testing. So again, the left is NDCG and the right is precision K. So in the x-axis, it also tells us the way of sampling these 5 drugs per cell line. We assume that doctors have some prior knowledge to prescribe the drugs rather than random sampling. So 1.0 means these 5 drugs are totally random sampled from the all the 250 drugs. And 0.5 means doctors have some prior knowledge and sample only from the top 50%, the most 50% of effective drugs. And 0.2 is 20%, 0.1 10%. So as can be seen that when we have this biased sampling, the top right line of KRI works better than the other regression-based methods, which decrease the performance when they see all these imbalanced data sets. However, we know that it's definitely not random sampling, but where are we? By which one is closer to the real scenario? We have different amount of gains here. So we look at our predictions, the top recommendations of our methods and the competitors. Where are they? So we can see that in all cases, most of the top 1 predictions are among the top 10% of the most effective drugs. So if we train a model and recommend the drugs and test it based on our predictions, we can probably end up in the middle of somewhere. But still, we don't know what is the real scenario in clinical data set. So we'd like to test on that. Finally, to conclusion, I think regression is not ranking when the prediction is not accurate. So one wrong prediction for one drug can ruin your whole ranking. So ranking is better when data set is sparse and imbalanced, as in clinic. The other way is that, but ranking answers the question which drug works better, but not how well a drug will work. So it could be that we rank the drug, but we don't know where's the bar of effectiveness. So practically, we think that regression and ranking should be jointly used. That you know where is the bar. You don't rank the not effective drug at all. So finally, thank you. I would like to thank. Okay, sorry. Yeah. Thank you.
Hi. So you evaluate your method on the CCLE data, for which you have all the response for all the drugs.
Yes, the JDSC, the slide bigger.
Yeah. Okay. Yeah. Sorry. But it's the same type of thing. You have the responses for all drugs, and as you mentioned in the clinic, usually, a patient will have received 1 drug or maybe a few drugs, but then you also have the question of there's several aspects of this. Is first, how will this translate when both on your training data you only have a small number of drugs given to each patient? And second aspect is I guess in the clinics, the order in which the drugs are given matters.
Yeah.
So
for the first question, if it's only 1 drug per patient, we can nothing to rank because we rank per patient. So we assume there are at least 2. So we choose 5, but but 2 or 3 is enough to rank the relationship between drugs. If you have enough samples, if you have tens of thousands of patients, and that would be enough to capture the relationship. For the ordering, yes, we didn't consider this yet, but Yeah, I think if you use one drug, you probably want to measure the gene expression because it's also changed from the one you used before. So probably practically you need more data sets or more features, as well as more responses to do the more accurate prediction. Yeah.
Okay, thanks.
When you were selecting the drugs that you have a bias selection, why do you think the other methods decrease the effectiveness?
So first, it's sparse. So I think there's many drugs have only 10 patients, and then the model is not accurate on these drugs, and then the imbalanced sampling means that the prediction also biased. So maybe this prediction of a few drugs will ruin the whole recommendation because they have. But for us, we only consider the top one, so it will not be affected. Yeah. Thank you.
Okay. It's time to speak.